Section: Introduction. In this section, we discuss the attention layer, which is essential in modern deep learning, especially within the transformer architecture. We can train attention efficiently by parallelizing computations across the sequence length, using matrix multiplications. However, the computational cost of attention increases quadratically, while the memory cost increases linearly with the sequence length. This presents a significant limitation and bottleneck for new and existing applications, despite improvements from optimized hardware implementations. To address this, linear attention substitutes the softmax kernel with a simpler linear kernel, specifically the dot product, allowing us to treat it as a linear recurrent neural network, RNN, with matrix-valued hidden states. This enables us to model sequences in linear time with constant memory. We can further parallelize linear attention training by dividing the sequence into chunks, which allows for subquadratic complexity while still being rich in matrix multiplications, leading to efficient hardware implementations. While earlier versions of linear attention did not perform as well as softmax attention, modern variants that incorporate data-dependent multiplicative gates, such as state space models like Mamba, have shown significant improvements. However, a fixed-sized hidden state in linear attention limits certain capabilities, like associative recall over longer contexts. Empirically, many recent linear RNNs claim to match or exceed softmax attention, but their performance often declines with longer contexts. We propose log linear attention as a compromise between linear and full softmax attention. Instead of using a single hidden state matrix, log linear attention maintains a growing set of hidden states, with the size increasing logarithmically with the sequence length. We demonstrate that with a specific growth function, log linear attention can be trained efficiently by replacing the causal mask in linear attention with a data-dependent hierarchical matrix, achieving log linear computational costs and logarithmic memory costs. Log linear attention serves as a general framework for sequence modeling and can enhance existing linear attention models. We apply this framework to two recent models, MAMBA2 and gated DeltaNet, and find that the log linear variants perform well compared to their original linear counterparts. In the background, we note that for an input sequence of length 24, softmax attention computes outputs for all time steps using key, query, and value matrices, which incurs high computational and memory costs for long sequences. Recent work has focused on efficient alternatives with subquadratic compute and sublinear memory, including linear attention and state space models. Many of these approaches can be summarized in a common equation, revealing shared characteristics across various models. Linear attention simplifies the process by removing the softmax operation, allowing for a parallel form that supports linear time, constant memory sequence modeling. However, vanilla linear attention lacks a forgetting mechanism, which is crucial in traditional RNNs. We can introduce this mechanism using a scalar gate, leading to a recurrence that also has a corresponding parallel form. Gated linear attention, which has gained popularity, includes models like RetNet and MAMBA2, utilizing data-dependent gates. We find that with a scalar gating factor, the structure of the gating matrix can still allow for efficient representations, which is not achievable with the full rank used by Mamba. Section Summary. In this section, we discuss the limitations of traditional attention mechanisms in deep learning, particularly their quadratic compute and linear memory costs, which hinder their application to long sequences. We introduce log linear attention as a more efficient alternative that maintains a growing set of hidden states, allowing for subquadratic compute and logarithmic memory costs, while demonstrating its effectiveness through case studies on existing models. Section: Linear attention with the delta rule. In this section, we discuss linear attention using the delta rule, specifically through a model called DeltaNet. This model updates its hidden state based on the delta rule. While the original version was purely recurrent, recent advancements allow us to parallelize DeltaNet across the sequence length by using a compact representation of householder matrices. This leads to a new parallel form. We note that certain matrices used in this process are lower triangular and consist of ones. Although one of these matrices is already lower triangular, we can modify another matrix to enhance the model's capabilities, resulting in gated deltanet. We find that linear attention with structured transition matrices is theoretically more effective for specific state tracking tasks compared to traditional linear attention with multiplicative gates. This makes these layers appealing for our log linear attention framework. Next, we explore long convolution sequence models, where the size of the convolution kernel matches the sequence length. Examples include the Toeplitz neural network and multi-hyena layers, which utilize a causal Toeplitz matrix generated by a long convolution kernel. Other models like H3 and hyena also fit into this attention style framework. While we can improve the decoding speed of these models, their memory usage remains linear, similar to softmax attention. However, some models, like S4, can be reparameterized to allow constant memory inference. We also mention attempts to simplify long convolution models into RNNs, but these still face memory limitations. We highlight the importance of the masking structure in determining computational and memory efficiency. Using an unstructured matrix can lead to performance degradation, making the structure of the masking matrix crucial for efficiency. In linear attention, we can compute in chunks, leading to a more efficient algorithm. Long convolution models can also leverage FFT to reduce costs. Our log linear attention mechanism introduces a specific structure to the masking matrix, allowing for logarithmic compute and memory costs. This approach modifies only the masking matrix, enabling us to generalize linear attention models with different structures. We demonstrate how to derive log linear variants of existing models based on our framework. We utilize a Fenwick tree-based method to partition input into segments of power of two sizes. This allows each position to summarize a range of past information, enabling queries to focus on a logarithmic number of hidden states. This structure emphasizes recent tokens and supports efficient decoding. For training, we show that this formulation corresponds to a structured masking matrix that leads to a parallel algorithm with favorable time and space complexities. Finally, we explain how log linear attention generalizes the simplest form of linear attention by encoding distinct memories across different time segments. We adopt a Fenwick tree structure for effective hierarchical segmentation, which helps us model recent context with higher resolution. Our partitioning scheme divides the input into disjoint buckets, allowing us to compute the output by separately handling each bucket and weighting it based on the input. This adaptive approach is essential for capturing multi-scale temporal structures. Section Summary. In this section, we explore DeltaNet, a linear attention layer that utilizes the delta rule for updating hidden states, and demonstrate how its parallelization can enhance efficiency. We also introduce log linear attention, which optimizes the masking structure to achieve logarithmic compute and memory costs, while employing a Fenwick tree-based partitioning scheme to effectively manage temporal context across different scales. Section: Parallel Form. In this section, we discuss the parallel form of our computations. While the original equation is conceptually clear, it mainly involves matrix vector products, which are not efficient on modern hardware that is optimized for matrix-matrix operations. To take advantage of hardware acceleration and allow for parallel computation across time steps, we reformulate the computation into a form that is more compatible with matrix multiplication. Here, we denote the level of a token at a specific time under the Fenwick tree partitioning. For simplicity, we do not explicitly mention dependencies when the context is clear. The matrix we refer to shows a structured low-rank pattern due to the Fenwick tree partitioning, and we explain how to utilize this structure to create a parallel training algorithm. For memory-efficient decoding, we perform incremental token-by-token decoding. We note that a specific value determines the index of the least significant set bit in the binary representation of time. The new hidden states are derived from a recurrence that reflects the core structure of the Fenwick partitioned memory. At each time step, the current memory term is placed into the finest resolution bucket, while all buckets up to a certain level are merged into a coarser resolution bucket. When the time is a power of 2, a new level is added, which helps maintain memory during inference. This decoding process is similar to the online update and query mechanism used in Fenwick trees. We also remark that the matrix we discuss is a lower triangular version of a hierarchical matrix, specifically of the HODLR type. When constructed using the Fenwick tree, it retains the recursive partitioning and low rank off-diagonal blocks characteristic of hierarchical matrices. This creates a link between log linear attention and hierarchical matrices, where the attention operator corresponds to structured matrix multiplication with a hierarchical matrix. We refer to this matrix as a quasi-hierarchical matrix, which is designed to support efficient recurrence. For our efficient training algorithm, we implement a chunkwise parallel approach for linear attention. This method divides a sequence into chunks and processes them in parallel while allowing information to flow between chunks when needed. This strikes a balance between fully parallel and recurrent forms, reducing the computational cost of global attention while enhancing sequence-level parallelism. We adapt efficient chunkwise computation techniques for linear attention to the log linear case. We observe that the matrix exhibits a low-rank structure in its off-diagonal blocks, allowing for a specific decomposition. Each block in a block diagonal matrix encodes interactions within chunks, and these blocks are lower triangular. The dependencies between chunks are managed through a series of linear attention passes. Thanks to the hierarchical matrix structure, each level simplifies to a computation involving a semi-separable matrix. When we have an efficient state-passing primitive available, inter-chunk computation requires only a limited number of invocations of this primitive, with each invocation costing a certain amount of time and memory. This method extends the classical scan algorithm into the hierarchical domain, which we call a chunkwise parallel scan. Unlike token-level scans that face memory bandwidth limitations, our chunk scan restructures memory updates into parallel operations across chunks. It performs independent scans for each memory level, which can be implemented using standard parallel techniques. Layer-specific weights are directly integrated into these scans, allowing for efficient and scalable computation throughout the hierarchy. Section Summary. In this section, we reformulate computations to optimize for hardware acceleration by leveraging a matmul-friendly structure, which allows for efficient parallel training and memory-efficient decoding using a Fenwick tree partitioning. We also introduce a chunkwise parallel algorithm for linear attention that balances computational costs while enabling greater sequence-level parallelism, utilizing the low-rank structure of hierarchical matrices to enhance efficiency. Section: Log linear generalizations of MAMBA2 and gated deltanet. In this section, we introduce log linear attention as a hierarchical extension of linear attention and explore its application to two specific architectures, MAMBA2 and gated deltanet. Both models utilize gating mechanisms that create a semi-separable structure in the attention mask. The key difference between them is how they parameterize the transition matrix. We maintain the original form of this matrix in both models while combining the attention mask with its log linear version. We call the resulting models log linear MAMBA2 and log linear gated deltanet. This approach demonstrates a broader principle. Any linear attention mechanism with structured memory can be adapted to a log linear version by integrating its attention mask with a log linear counterpart. For implementation, we developed a chunkwise parallel scan algorithm in Triton. Our custom kernel for log linear MAMBA2 outperforms FLASHATTENTION2 for sequence lengths over 8,000. The throughput during full training varies by model architecture. Notably, log linear MAMBA2, which includes MLP layers, exceeds transformer throughput at 32,000, even with additional layers like depthwise convolutions that the transformer lacks. We provide further details in the relevant section. In our experiments, we first assess multi-query associative recall, MQAR, a benchmark for evaluating recall capabilities. We train for 100 epochs on a dataset of 10,000 samples, focusing on the non-gated deltanet variant, which performs best on MQAR. Our models consist of two layers, each with a specific number of heads. We observe that as the sequence length and number of key-value pairs increase, DeltaNet's performance declines significantly, while log-linear DeltaNet maintains high accuracy. Softmax attention achieves full accuracy across all settings. For language modeling, we conduct pre-training from scratch using 50 billion tokens on the long data collections dataset, with a sequence length of 16,000. All models have 21 layers and a hidden size of 1,536. We compare a transformer with 16 attention heads, a modified Mamba 2 with 48 heads and MLP layers, and a gated DeltaNet with 6 heads. The parameter counts for these models are 693 million for the transformer, 802 million for Mamba 2, and 793 million for gated DeltaNet. For the log-linear variance, we add a linear layer on top of the hidden states to compute per-head values, which increases the parameters slightly for MAMBA2 and gated DeltaNet. Since both Mamba 2 and gated DeltaNet have more parameters than standard transformers, we also include a parameter-matched transformer variant with 24 layers for comparison. Section Summary. In this section, we introduce log-linear generalizations of the Mamba 2 and gated DeltaNet architectures, which enhance their attention mechanisms by incorporating a log-linear variant of the attention mask while maintaining their original transition matrix structure. Our implementation demonstrates that these log-linear models outperform traditional methods in terms of throughput, especially at longer sequence lengths, while also exploring the implications of using different matrix structures in recurrent neural networks. Section: Standard Benchmarks. In this section, we evaluate our models using standard benchmarks, including wiki-text perplexity and various zero-shot common-sense reasoning tasks. These tasks involve short contexts, so we expect the log-linear models to perform similarly to the linear ones. We find that log-linear Mamba 2 outperforms its linear version in perplexity and half of the reasoning tasks, while log-linear gated DeltaNet shows even greater improvements, surpassing its linear counterpart in perplexity and nearly all reasoning benchmarks. It also outperforms a layer-matched transformer in all metrics and a parameter-matched transformer in half. Next, we analyze the model's loss at each token position to assess its ability to manage long contexts. If the loss decreases as we move through the token positions, it indicates effective use of the full context. We use 39 million tokens from BOOK3 and apply a running average for better visualization. We observe that both Mamba 2 and gated DeltaNet in their log-linear forms consistently reduce the loss across positions, suggesting better long-range context utilization. However, there remains a performance gap when comparing gated DeltaNet to the parameter-matched transformer. We also utilize the needle in a haystack benchmark, where the model retrieves a specific value from a long context. In simpler tasks, log-linear Mamba 2 outperformed its linear version in most metrics, while gated DeltaNet improved in some areas. For more complex tasks, both log-linear models showed significant improvements. In our evaluation of real-world recall-intensive tasks, we find that log-linear Mamba 2 improves on about half of the tasks, while log-linear gated DeltaNet consistently matches or exceeds its linear counterpart in nearly all tasks except one. Finally, we assess the models on long bench and find that both log-linear Mamba 2 and gated DeltaNet outperform the baseline in most evaluation tasks. In our discussion, we note that while log-linear attention shows improvements in many cases, there are still tasks where it does not surpass linear attention. Due to resource limitations, we could not explore different parameter settings, which might yield better results. We also recognize a significant performance gap compared to transformers across all benchmarks. The complexity of log-linear attention is higher, as it requires more intricate computations. Additionally, the use of Fenwick tree partitioning introduces an inductive bias that may not be optimal for every application. Future work could investigate more flexible structures while maintaining computational efficiency. Section Summary. In this section, we evaluate our models on various benchmarks, finding that log-linear variants generally outperform their linear counterparts, particularly in perplexity and common-sense reasoning tasks. We also discuss the challenges and limitations of log linear attention, including its engineering complexity and performance gaps compared to transformers, while suggesting that future work could explore more flexible structures for improved results. Section: Related work. In this section, we discuss related work in the field of matrix multiplication, which is essential for modern deep learning. Current architectures usually include a token mixing layer and a channel mixing layer, both relying heavily on matrix multiplications. We note that researchers are increasingly exploring the use of structured matrices instead of dense ones. For channel mixing, we see efforts involving butterfly matrices, monarch matrices, and more recently, block tensor train matrices. In token mixing, linear attention models and their variations have been highlighted. We generalize these methods by applying low-rank structures to semi-separable matrices, which allows for efficient recurrent inference and encompasses many recent recurrent models. Additionally, we observe that some research focuses on sparse attention patterns, like sliding window attention, and various hybrid methods have emerged. In our work, we present a hierarchical matrix formulation that facilitates state expansion while ensuring efficient training and inference on hardware. Previous studies have aimed to reduce the quadratic cost of attention to log linear time complexity. For instance, Reformer uses locality-sensitive hashing to cluster similar queries and keys efficiently. Multi-resolution attention takes a hierarchical approach, refining attention scores from coarse to fine, while fast multipole attention adapts classical methods to model long-range interactions effectively. We utilize the Fenwick tree data structure, which allows for efficient prefix sum calculations and updates in logarithmic time, to create an effective attention layer for both training and decoding. While other works also use hierarchical matrices for attention, their methods are fully parallel and designed for shorter sequences. In contrast, our approach employs a chunkwise parallel strategy with a custom Triton implementation optimized for long sequence training. Our design, derived from linear attention, imposes a structured matrix constraint that ensures efficient inference and training complexity.